Welcome to G Fun Facts Online. When humanity looks toward the stars, the imagination immediately leaps to roaring engines, sleek spacecraft, and the profound silence of the cosmic void. Yet, beneath the cinematic romance of spaceflight lies a grueling, unforgiving battle against the laws of thermodynamics and fluid mechanics. For decades, the ultimate bottleneck in deep space exploration has not been the lack of powerful rockets, but a deceptively simple question. How do you store the coldest, most volatile, and most efficient fuel in the universe while floating in the zero-gravity vacuum of space? The answer lies in the highly specialized and fascinating field of cryogenic fluid dynamics. Specifically, the containment, management, and utilization of liquid hydrogen in microgravity environments is the keystone technology that will dictate whether humanity successfully establishes a sustained presence on the Moon, ventures onward to Mars, or remains tethered to low Earth orbit. As we enter the Artemis era and look toward crewed interplanetary missions, mastering the tempestuous behavior of liquid hydrogen in space is no longer just a theoretical pursuit, it is an absolute, mission-critical necessity. To understand the immense effort poured into cryogenic fluid dynamics, one must first understand why engineers are so obsessed with liquid hydrogen. In the realm of rocket propulsion, efficiency is measured by specific impulse, a metric that dictates how much thrust is generated per unit of propellant consumed. Think of it as the miles per gallon rating for a rocket. When combusted with liquid oxygen, liquid hydrogen yields the highest specific impulse of any practical chemical bipropellant system known to science. It was the lifeblood of the Saturn V upper stages, the Space Shuttle main engines, and is now the primary propellant for NASA's Space Launch System and various next-generation heavy-lift architectures. Furthermore, liquid hydrogen is the sole propellant required for nuclear thermal propulsion, a revolutionary technology planned for future Mars transfer vehicles, which uses a nuclear reactor to heat and expand hydrogen to generate thrust without combustion. But liquid hydrogen comes with a staggering caveat. It is a cryogenic extremity. To keep hydrogen in a liquid state, it must be chilled to a bone-numbing 20 Kelvin, which is negative 253 degrees Celsius, or negative 423 degrees Fahrenheit. At these temperatures, the ambient warmth of deep space, the heat radiating from the spacecraft's own electronics, and the thermal reflection of Earth or the Moon are enough to violently boil the fluid. On top of its extreme temperature requirements, liquid hydrogen is the lightest liquid in the universe. Its incredibly low density requires massive storage tanks to hold enough mass for a journey. It is also highly pervasive, capable of leaking through microscopic atomic gaps in solid metals, and it causes hydrogen embrittlement, a chemical process that actually weakens the very metallic structures designed to contain it. Taming this beautiful beast on Earth is hard enough, but taming it in the weightlessness of space is one of the most complex engineering challenges of the 21st century. If you boil a pot of water on Earth, the physics are entirely predictable. Gravity provides a distinct up and down. The heavier, denser liquid settles at the bottom of the pot, while the lighter, heated vapor bubbles rise to the top due to buoyancy. This separation of liquid and gas makes extracting fuel from a tank on Earth relatively simple. You just place a drain hole at the bottom and let gravity do the work. But in the microgravity environment of orbital spaceflight, this intuitive reality completely breaks down. Without gravity to separate fluids by density, buoyancy ceases to exist. The empty vapor space in a tank, known as the gas ullage, no longer sits neatly at the top. Instead, surface tension, capillary forces, and intermolecular adhesion take over as the dominant physical forces shaping the fluid. In a spacecraft fuel tank, liquid hydrogen tends to cling to the tank walls due to capillary action, while the gaseous vapor forms a massive, free-floating spherical bubble in the center, or even worse, a chaotic matrix of thousands of smaller bubbles distributed unpredictably throughout the liquid. This creates a terrifying scenario for a rocket engine. Rocket engines rely on turbopumps, which feed propellant into the combustion chamber at ferocious speeds. These pumps are precision-engineered to pump liquid. If they ingest a pocket of gaseous hydrogen instead of liquid, the pump loses its mechanical resistance. It can cavitate, overspeed, and violently explode, instantly destroying the spacecraft. Therefore, knowing exactly where the liquid is and ensuring only pure, bubble-free liquid reaches the engine is a life-or-death problem that requires masterful fluid dynamics. Compounding this issue is the menace of slosh dynamics. Spacecraft are not static objects. They maneuver, rotate, dock, and experience thruster firings. Every time a spacecraft moves, the thousands of gallons of liquid hydrogen inside its tanks move with it. This phenomenon, known as sloshing, represents a massive headache for aerospace engineers. In terrestrial vehicles, sloshing is mitigated by gravity quickly dampening the fluid motion. In microgravity, a disturbed fluid can continue oscillating for a very long time, driven by its own inertia and the total lack of gravitational damping. This internal movement of mass can aggressively shift the spacecraft's center of gravity, causing attitude control systems to overcompensate, potentially sending the entire spacecraft into an uncontrollable, dizzying spin. Furthermore, slosh dynamics actively sabotage thermal management. When the ultra-cold liquid hydrogen splashes against the warmer upper sections of the tank wall, which are usually exposed to solar radiation, it rapidly absorbs heat. This process is known as slosh-induced thermodynamic phase change, and it dramatically accelerates the evaporation of the liquid into gas, rapidly raising the internal pressure of the tank. Recent computational fluid dynamics models and microgravity experiments, such as those utilizing drop towers and parabolic plane flights, have been absolutely essential in understanding these complex, non-linear fluid behaviors. They have revealed that even minor, rhythmic excitations can cause massive disruptions to the liquid-vapor interface. Even if a spacecraft is perfectly still, the slow, creeping ingress of heat is strictly inevitable. No insulation in the universe is perfect. As heat from the sun or the spacecraft subsystems leaks through the tank walls, it warms the liquid hydrogen. On Earth, natural convection would cause the warmer liquid to rise and mix with the colder liquid, creating a relatively uniform temperature distribution throughout the tank. In space, the lack of convection leads to a dangerous condition called aggressive thermal stratification. Deep pockets of cold liquid remain isolated at the center of the tank, while a superheated layer of liquid forms right against the tank walls and at the liquid-vapor interface. This superheated boundary layer rapidly evaporates, increasing the gaseous pressure inside the tank. This self-pressurization creates a ticking time bomb. If the pressure exceeds the structural limits of the tank, the vessel will rupture. Historically, the only way to prevent this catastrophic failure was to open a valve and vent the excess hydrogen gas straight out into space. While this keeps the tank safe and relieves the pressure, it means the spacecraft is continuously bleeding its own precious fuel. For short missions, such as the Apollo lunar voyages or the space shuttle flights in low Earth orbit, venting was an acceptable compromise. The missions were brief enough that the fuel lost to what engineers call boil-off was factored into the mission margins. But for the modern era of deep space exploration, venting is an absolute mission killer. Consider a crewed mission to Mars. To successfully reach the red planet and return home, a spacecraft might require around 38 tons of cryogenic fuel. Using traditional Apollo-era venting systems, a spacecraft could lose up to 18 tons of liquid hydrogen per year simply to boil off. By the time the crew actually arrives at Mars, their return fuel would have literally vanished into the ether. Carrying an extra 38 tons of fuel just to compensate for the loss is financially unfeasible and mathematically ruinous to the rocket equation. To conquer the deep solar system, NASA, the European Space Agency, and private aerospace entities are furiously pursuing the holy grail of cryogenic fluid management, known as zero boil-off technology. The ultimate goal of zero boil-off is to create a closed-loop thermodynamic system where not a single drop of propellant is lost to evaporation, no matter how long the mission lasts. Achieving this requires a brilliant, synergistic combination of passive and active thermal management systems. The first line of defense is passive. Tanks are wrapped in dozens of layers of multi-layer insulation, which consists of ultra-thin mylar sheets coated in reflective aluminum, separated by non-conductive netting. This insulation operates in the hard vacuum of space to effectively eliminate radiative and convective heat transfer. Furthermore, advanced spacecraft architectures cleverly utilize the vehicle-own geometry to physically shade the fuel tanks from the blazing sun. Specialized low-conductance composite struts are used to physically attach the ice-cold tank to the warm spacecraft body, minimizing the conductive heat leak through the metal. While passive systems drastically slow the heat leak down, active systems are required to actually reverse it. Zero boil-off systems utilize mechanical cryocoolers, which are essentially ultra-high-tech, space-rated refrigerators. These incredible devices pump a refrigerant gas, like helium, through a dense network of tubes wrapped tightly around the hydrogen tank, creating what is known as a broad-area cooling shield. The cryocooler literally extracts the heat that has leaked into the tank and pumps it outward, radiating it safely into deep space via exterior thermal radiators. Recent architectural studies for nuclear thermal propulsion vehicles indicate that utilizing a two-stage, 20 Kelvin class, zero boil-off cryocooler system could completely eliminate the 16,500 kilograms of boil-off fuel that would otherwise naturally occur over a 2-year orbital loiter period. But because microgravity prevents natural convection, simply chilling the outer walls of the tank is not enough. The cold fluid must be actively mixed with the warm fluid. This is achieved through thermodynamic vent systems and active jet mixing. A small specialized pump draws cold liquid from the deep heart of the tank and sprays it as a high-velocity jet straight through the hot ullage gas and against the tank walls. This forced convection acts like a storm inside the tank, breaking up the thermal stratification, immediately condensing the hot vapor back into a dense liquid, and successfully lowering the overall tank pressure without venting a single molecule of fuel. To perfect these systems, researchers like Dr. Mohammed Qasemi at Case Western Reserve University have led groundbreaking, long-term experiments aboard the International Space Station. The zero boil-off tank experiments utilize small-scale tanks filled with special simulant fluids to precisely map out exactly how fluid jets interact with the strange, spherical liquid-vapor interfaces found in microgravity. The latest iteration of these experiments adds non-condensable gases, like the helium that is often used to pressurize rocket fuel systems, into the mix, measuring exactly how they alter the complex evaporation and condensation dynamics of the fuel. While zero boil-off technology beautifully handles the temperature problem, engineers still need to ensure that the engine pumps only swallow pure liquid hydrogen and absolutely no gas. Enter the propellant management device. Propellant management devices are intricate, static, internal metal structures built directly inside the fuel tanks. Because they have absolutely no moving parts, they are incredibly reliable. They rely entirely on the microscopic physics of capillary action and surface tension to seamlessly manipulate the fluid. By carefully designing geometric metal veins, enclosed galleries, and highly porous titanium sponges, engineers can create a powerful capillary wicking effect. This effect intentionally draws liquid hydrogen directly toward the engine drain port while simultaneously repelling any dangerous gaseous bubbles. One of the most critical components of a propellant management device is the capillary sieve or screen. These microscopic, tightly woven meshes utilize the natural surface tension of the liquid hydrogen to create an invisible, impenetrable barrier. Liquid can easily flow through the tiny holes in the mesh, but once the mesh is wet, the surface tension of that liquid stretches across the pores and physically prevents gaseous bubbles from penetrating it. During the historic Artemis I mission, the Orion spacecraft European Service Module successfully utilized highly advanced capillary sieves developed by John Crane and Ariane Group. These bespoke sieves were engineered to perfectly separate the liquid and gas phases inside the propellant tanks, enduring brutal launch vibration tests and ensuring unrestricted, pure liquid flow when the spacecraft needed to execute vital, precision maneuvers around the Moon. However, for future architectures handling truly massive volumes of cryogens, static devices might not be enough. Advanced active concepts are currently in rapid development, such as the Dynaswirl cryogenic phase separator. This fascinating device utilizes rotational fluid dynamics to artificially induce a localized centrifugal gravity field right inside a transfer pipe. As the fluid swirls at high speeds, the heavier liquid hydrogen is forcefully thrown to the outside walls of the tube, while the lighter, dangerous vapor bubbles are pushed directly into the center, allowing the pure liquid to be cleanly and safely extracted from the outer edge. The ultimate test of all this cryogenic fluid dynamics is on the immediate horizon. To land massive payloads on the Moon and eventually Mars, the harsh mathematics of rocket equations dictate that we simply cannot launch a fully fueled, massive deep space vehicle directly from the surface of Earth. We must launch the hardware dry, and then separately launch the heavy fuel. This introduces the revolutionary concept of the orbital propellant depot, effectively a cosmic gas station floating in low Earth orbit. Future spacecraft, such as the SpaceX Starship human landing system, will launch into orbit nearly empty to save weight. Following this, an entire fleet of tanker spacecraft will rendezvous with the depot or the landing system to transfer hundreds of tons of liquid hydrogen and liquid oxygen in the total absence of gravity. Transferring cryogenic liquids in space is a violently chaotic process. When the ultra-cold liquid hydrogen, sitting at 20 Kelvin, hits the relatively warm transfer pipes and receiver tank of a new spacecraft, the liquid instantly boils upon contact, violently flashing into expanding gas. This chaotic process, known as chill-down, can cause massive, dangerous pressure spikes and create stubborn vapor locks that completely block the flow of propellant. To achieve true no-vent filling in microgravity, highly complex automated fluid dynamics models must flawlessly orchestrate the entire transfer. The receiving tank must be incredibly slowly pre-chilled, and thermodynamic vent systems must carefully and continuously manage the pressure without exhausting the precious hydrogen into the void. Successfully demonstrating cryogenic in-orbit ship-to-ship refueling is widely considered the single most critical technological hurdle standing between humanity and a sustainable, thriving lunar economy. The dream of a multiplanetary future is not just written in the loud fire of rocket engines, but in the silent, invisible dance of sub-zero fluids floating in the dark. Cryogenic fluid dynamics is a unique discipline where quantum mechanics, thermodynamics, and astrophysics violently collide. Every single time a thruster fires perfectly in the deep vacuum of space, it is the direct result of decades of agonizing research into slosh dynamics, capillary forces, and microgravity phase changes. By building massive orbital fuel depots, perfecting zero boil-off cryocoolers, and weaving intricate capillary sieves, engineers are literally rewriting the rules of how fluids behave in the universe. Taming liquid hydrogen is an engineering marathon of truly epic proportions. But as we look eagerly toward the Artemis lunar landings and cast our eyes further outward to the rusted sands of Mars, one undeniable truth remains certain. Whoever controls the ice-cold heartbeat of the spacecraft ultimately controls the solar system. Thank you for joining us on Fun Facts Online. Keep looking up and stay curious.